Hello everyone, in this series, we will be working on Project Euler, which has published weekly problems since 2001, counting almost 800 of them and more than 1 million members. We will be talking about the theory that lies behind each problem, and the method that can be used to programmatically solve it. Sadly, we won't be able to go past the 100th problem in this series, as giving answers is not allowed by the website past this point. But we already have a lot of material to work on for sure. But for now, let's get a look at problem 76, which is a pretty good start to the series in my opinion. It states that it is possible to write 5 as a sum in exactly 6 different ways. And we are asked to compute the number of ways we could do the same with 100. What we are asked here is called the partitions of an integer which is written as p of n. Except we need to subtract 1 from it since we are not counting the number itself, whereas the partition function does count it. So, we are searching for p of 100 minus 1. But actually, a recurrence relation can be found to simplify the work. Let's start with the pentagonal theorem of Euler, which states the following. This may not seem very helpful, but we can also mention another identity, involving the partition function, and its generating function. Do you notice something here? Well, if we multiply the two identities, we obtain 1. So let's multiply everything all together, which gives us 1 on the right side. Now if we develop those sums, we get a polynomial with clear coefficients, and this polynomial must be equal to 1. As 1 is actually a polynomial with infinite zero coefficients, we can set each coefficient inside our sum to be 0. This permits us to write that p of n equals p of n minus 1 plus p of n minus 2 and so on. Finally, here is the aimed recurrence. Now that we have a relation using recurrence, let's make a grid of the values of the partition function from 0 to 99. Let's start from 0, knowing that p of 0 is 1. Here, we need to compute this for every k that satisfies the inside being positive, because otherwise, we would need the partition of negative numbers. 100 is honestly a really small number and it is thus really easy to compute every partition until that point to use the recurrence. Let's repeat this process for all the numbers here, and we'll be done. Let's start slowly with the first 10 values. Then let's speed it up a bit for the next 20. And even faster for the remaining ones. Here, we stopped at the partition of 99, so you could either use the values shown here, along with the relation, or make your own program. In any case, thanks for watching, and I hope to see you soon.